We're thrilled to welcome Michael Schutz, who's an associate professor of music cognition and percussion in the School of the Arts and directs the Maple Lab, which researches music, acoustics, perception, and learning. While maintaining an active career as a musician, conducting the McMaster Percussion Ensemble, and serving on faculty at the Honors Music Institute in Pennsylvania. Thank you so much for joining us, and we're incredibly excited to hear this talk.
My pleasure. So I'm really excited to be here because the Spark series is a great opportunity to learn about so many new good ideas. And we've seen some amazing different topics throughout the year. And when I got invited to give this talk, I was trying to think, how can I distinguish myself from this whole field of excellent ideas? And I thought maybe the best way to stand out is to actually, instead of a good idea, starting off with a really, really terrible one. So here's one of the worst ideas that I've ever heard, courtesy of America's favorite inventor, Homer Simpson.
Now, here's my everything's okay alarm. This will sound every 3 seconds unless something isn't okay. Turn it off.
So there's a lot of reasons why you might find that to be not the best idea. It's not particularly helpful, it's not particularly informative, and frankly, it's pretty annoying. But the thing that I find to be the worst idea about that is, as a music professor, I'm just bothered by the fact that it's a terrible, terrible sound. See, I love researching sound. My lab, we analyze sounds, we synthesize sounds, and we explore how our minds process those sounds. And so when I saw that example from Homer Simpson, among other things, I thought, that is a really bad example of sound design. Now, we'll come back later on to why I'm starting off this talk with a clip from Homer Simpson, but believe it or not, that same bad sound is actually being used, or sounds that are similar like that, in hospitals all around the world, and it's leading to incredible problems for public health, including patient deaths. Now, the way we got interested in this issue is that my lab at McMaster University takes a different approach to studying music perception and music cognition. So like a lot of music psychology labs, we use sound and music to try and understand how the mind works. But we complement that with a strong focus on trying to also use scientific approaches to understand how sound works. And I think the experiments that we're doing that I'm the most interested in are the ones that really draw from both areas. And it's the second one about really getting into the trenches, about looking at sound, that I think is important, because oftentimes that gets overlooked. In quest about understanding sound perception, we're often focused more on how those sounds can tell us about how the mind works. And that oversight, I think, has led to some really important problems. So my lab right here on campus, which I've finally been able to go to as of this week and see my students again, is hard at work trying to explore how we can use our knowledge of musical sounds to help improve the kinds of alarms that are used in hospitals all over the world. Now, if you've ever spent some time playing around with sound or recording, you're probably familiar with a little bit about the ways in which computers represent sound. And so if we zero in on this computer screen here, you can see we have a fairly common way of looking at sound files, where what we're looking at is the energy in the sound over time. So if you're recording a friend playing, or even watching some of your favorite music being played on some devices, you might see some lines moving up and down that are representing how much sound energy we have over time. Now we can actually zoom in there and pull out individual notes from specific instruments. And so say this recording session here involves a piano and a cello. If we looked at those individual notes, we would see something like this. Now the way that energy changes over time tells us a lot about how the instruments are structured. So the piano, when you press a key down, has a hammer that hits a string, and the energy goes into the string and gradually decays. And that's why when we look at that sound profile, we see a lot of energy at the beginning, which decays away. Now, when you draw a bow across a string, like on the cello, the sound will grow and change and ebb and flow over time. So different instruments produce shapes of sound with these very different energy profiles. And scientists quantify this and discuss it using the term amplitude envelope. Now, amplitude envelope is really just a measure of how much amplitude of energy we have over time. So it's essentially like just half of those sounds that I'm showing you on the left. So on the top I have an amplitude envelope from a sound from a cello, and on the bottom an amplitude envelope from the sound of a piano. And these are produced by natural instruments. So you can see all the bumps and changes in there because there's a lot of temporal complexity. Now, we can also synthesize these sounds. And if we synthesize them in a lab, you get a sound that looks more like this if you're synthesizing a piano note. Now, I call it a percussive tone because, well, I'm a percussionist, but it comes from a percussive event, an impact event. And I got very interested in these many years ago when I did a study on percussion playing where I found that percussive tones are actually processed in a very different manner than the kinds of sounds that are often used in research. Because I found an example of a situation where musicians can actually use gestures to trick audiences into hearing certain things that are not possible to do with the instrument alone. And the surprising thing from this, aside from the musical implications, is that the scientific community was very much in agreement that that particular pattern of processing could never happen. And in trying to figure out what was going on, I realized that a lot of auditory research is done with sounds with an amplitude envelope that I call a flat tone. So a sharp onset and a long sustain and a quick offset. Now, we can synthesize sounds with any kind of shape. And so I'll play for you now just a sample of this common sound used in many experiments. What's useful about this from a scientific perspective is that it's very controlled. Aesthetically, I find that a little bit offensive, but that's the main way we've been studying the auditory system for some time. Now we can take that same sound and put a percussive decay on it, and it sounds much, much more pleasant. Now, most of the time in the lab, we're not really worried about the aesthetics of the experiment. We're worried about the precise control over the sounds that we're using. But this oversight of aesthetics has actually led to some significant problems that are affecting a wide range of people in different industries. Because those flat tones up top are similar to the kinds of sounds that are used around the world in auditory interfaces. Now, you probably haven't thought a lot about interface design before today, but I can guarantee that you often use a visual interface. So that smartphone you've got in your pocket or the computer screen over which you're watching this lecture is a great example of a visual interface. It's a way for us to communicate with technology using our eyes. Now, consumer-facing products use a lot of visual interfaces because they can be effective in many situations where we need to get a lot of information quickly. Auditory interfaces are different. They're ways in which we connect with machines using our ears. Now, these are very important in a variety of safety-critical applications, like engineers driving trains or pilots flying planes, because in these situations, the individuals have to keep in touch with a wide range of technology while keeping their eyes ahead. And so situations where our visual attention is needed elsewhere, auditory interfaces are particularly important, and oftentimes we find these as safety-critical situations. Now, the interesting distinction between those safety-critical interfaces and the visual interfaces in consumer products is that for consumer products, essentially we vote with our wallets. And so if phones and computers use really, really terrible sounds, you would pick that up when people stop buying those products. But we don't let consumers control the sounds on the trains or the planes in which they're flying because their purpose there isn't to delight. Their purpose there is to inform. And so because we need the standardization, committees will decide the sounds that are used in these situations. And the problem is that the committees have steered us to sounds that are really problematic. For example, in hospitals across Ontario right now, patients are flooded with sounds like these. I can barely stand listening to those sounds for 10 seconds. I have no idea how doctors and anesthesiologists and even patients are subjected to those for days or weeks on end. My mother-in-law once remarked that after retiring from a career in nursing, she felt the hospitals were a beeping hellscape, and I thought that was a pretty good way of summarizing the current state of sound design. Now, I have a colleague who's an anesthesiologist who describes how in situations he's routinely faced with these alarms blaring in his ear, and it's often not actually giving him any useful information. For example, when he's intubating, sticking a breathing tube into a patient, this alarm starts going off telling him the patient isn't breathing, which he knows because he stopped the respirator to get the tube into their throats. And so he's not able in this moment to get the other information he needs or have communications with his colleagues because this unhelpful and annoying alarm is just blaring away. Now, the problem with this is that in some situations, medical staff turn down or even turn off the alarms so that they can communicate during complex operations. And in some situations, this has led to tragic consequences. For example, one well-known situation, a team turned off medical alerts that were designed to let people know when the patient had stopped breathing because they had to temporarily turn off the ventilator to get a clear X-ray image during the procedure. Now, when something happened and they forgot to turn this back on, because they had silenced the alarms, no one noticed until it was too late. and that patient died. And unfortunately, that tragic incident is not isolated. And in fact, an FDA survey identified 566 deaths related to these alarms in a 4-year window. So the bottom line is that the problematic sounds here are not just annoying, but they can actually end up costing patients their lives. So if you remember nothing else from this talk today, I hope you remember that bad sound design can actually cost you your life. And it's not just these most extreme situations. They also cause all sorts of other problems for patient recovery and for the medical team to communicate. So the Emergency Care Research Institute, ECRI, puts out a list of their top 10 health technology hazards every year. And alarms have made this list more often than not over the past decade, twice in the #1 hazard spot. So the problems with these alarms are widely recognized and well known. Just to give you a few of them here, they're difficult to learn, they're hard to recall in terms of their associated meaning, and one thing that I'm really fixated on now is the fact that they're annoying everyone in that hospital in those operating rooms. So when I first started getting interested in this issue, there were 3 questions that bubbled up that I find can often be somewhat misleading as I go through the work that my team is doing now. So I just wanted to take a moment and address each of those one by one. The first is that if these sounds are so bad, why not use a visual interface? We can communicate over a screen. And if we're using sounds and there's trouble with learning the sounds, well, why not just use a speech alarm? That would be much easier to remember. And then finally, one that comes up more and more recently is that, well, hold on. If I'm in the hospital and there's a medical problem, well, isn't annoying good? Because I'm not there to be entertained, and I don't really care if the doctors are annoyed. If something's really going wrong, I want people to know immediately. And I think these are all important questions that we need to address before we can get into the work that we're doing now to try and improve the sound. So in terms of the visual displays, there's many situations like intubating a patient where it's important for surgeons and physicians to be able to keep their eyes on the patients or monitoring their hands or other things that they're doing. So in these situations, auditory interfaces allow them to keep connected with the updates that are critical while they're keeping their eyes where they need to be. And there's similar issues with the benefits of auditory interfaces when nurses are monitoring multiple beds in a hospital ward. So this is one reason why there's so much interest in developing auditory alerts in hospitals. Okay, so the next question is, well, if it's hard to remember these, why not just use speech alarms? And if there's problems, the machine could simply speak them about a blood pressure issue or there's challenges with the oxygenation. So there's many reasons why speaking the alarm is problematic. Research has shown that tone sequences are actually faster to be recognized, and if we want to have standardized systems that can be used across the world, it's good to move beyond languages. But the other thing is that it's actually important in many situations to shield patients from what the warnings are. So if you're lying in a hospital bed and the machine keeps saying there's a blood pressure issue over and over again, you might develop a blood pressure issue just from your concern over what the machine is saying. So for these and other reasons, it's good to have a series of sounds that are helpful and useful for communicating that don't require specific language. Now the last question is one that comes up quite a bit. Isn't annoying actually good? I mean, if I'm sitting there in the hospital bed and something terrible is happening, I want to make sure people know about it immediately. And so this is where I think we actually get into some language problems with the way we talk about these issues. Because we'll often use the term auditory alarms, but really what we're talking about here is an auditory interface, which is a very different thing than an auditory alarm. The problem with alarm is it refers accurately to situations where urgent action is needed. So if you think about a fire alarm, that doesn't go off very often, but when it does, you need to get out of that building immediately. And that's actually very different and in some ways the exact opposite of the situation of these machines in hospitals. Because studies have shown that patients can generate hundreds of alarms per day and very, very few require urgent critical action. So when we're flooded with these sounds and the sounds seem to be built to be annoying, and a lot of them aren't showing an immediate problem, there's a natural tendency to turn them down or tune them out because we're just filling our hospitals with this terrible sound. So it's important to recognize that the goal here is to design sounds that are communicative, and that doesn't necessarily mean that they're annoying. So now that we've covered these 3 questions, I want to share with you the question that keeps me up at night, which is this. For this industry with these massive public health implications, which is valuated by Industry Canada at over $6 billion a year, why is it that we continue to insist on using terrible sounds that seem to be no more sophisticated than the ones shared with us earlier by Homer Simpson. Like I said before, my background is in music and psychology, and I don't really have any background in medical research, or at least not before I got involved with this. So my entry into this field came from an unlikely conversation at a conference at Vanderbilt University many years ago when the Society for Music Perception and Cognition met there. So I had this medical doctor who tracked me down on a break, who was very interested in all this work that I'm doing on, structure of musical sounds, and he's involved with this international effort to redesign alarms in hospitals. And he pointed out that, I spent a lot of time looking at problems with the flat sounds versus more natural sounds, and he shared with me that the sounds used in these medical devices are essentially mandated to be these flat tones. And he's now in an ICU listening to these for 40, 50, 60 hours a week, just flooded with the terrible sound. Now, a lot of doctors are in that situation. What's different about Dr. Schlesinger is that before he went to medical school, he did an undergraduate degree in music. So he has spent years intensively focusing on sound and is very aware that sound can be informative and meaningful without being so bloody annoying. So this sparked a very interesting and fruitful collaboration that continues to this day, and I'll be happy to keep working with him as long as he'll keep coming to the lab. So he shared with me some sounds that are used in hospitals a lot, which are defined by standards set by the International Electrotechnic Commission, the IEC sounds. And here's 4 examples. I played these on a grand rounds talk for a hospital once and was absolutely horrified to realize that most of the doctors there didn't actually remember the associations of these alarms. And as I looked more into the issue, I realized the problem is widely known, not just in the research community, but in the medical community, where one of the original designers of these alarms published what I believe is the first peer-reviewed apology, where he quoted from the Bible and begged for forgiveness from his colleagues for having inflicted these terrible alarms on the community through these standards. Now, the problem with standards is that once we have them set, it becomes difficult to change them because people have learned certain ways of, recognizing the sounds. And so what my team is doing now is making a tweak to the complexity of the sound through its temporal structure that allows us to keep the same pitches and the same sequences and just make the individual notes much more palatable. So if we look at the fine level structure of these sounds here, these alarms are built now basically entirely on flat tones. And so what we're doing is just changing the shape of individual notes to make each one more percussive, more musical. So we get some transformations from a sequence like this to this. It's a small change from an acoustic perspective. It's actually very easy to synthesize the sounds in this way, but it's a big change in the approach of these things because auditory interfaces have essentially by default just been using flat tones for many years. So in our experiments here, I took sounds and shaped them with this temporal structure. And we used 2 kinds of spectral structures here, meaning the bass sound. The first one was just a pure tone, like you might hear from a tuning fork. And the second one had overtones, more like musical instruments. And it was helpful to test these because sounds with overtones are actually better in these medical environments because they're less likely to be masked or covered up by other sounds. Nonetheless, we didn't know if that would make them more annoying, so we designed a couple experiments to try and tease this apart. Now, our main question here is whether sounds with these more musical temporal structures and musical shapes are going to be less annoying. But it's also important in a medical context to know whether they're harder to learn or recall, because it's not going to help patient care at all if the sounds are better, but now people can't remember what the messages mean. So we set up an experiment where we put participants in one of 2 conditions. Either they heard our alarms in the flat tones, similar to the existing alarms, or they heard these alarms with the percussive tones. In the study phase, we simply played the sound for them and told them the associated alarm. In the training phase, we then played the alarm and asked them to give the associated message. We gave them feedback on whether they were right or wrong, and also played that sound again just to reinforce it. Afterwards, participants got to go to their favorite part of the experiment where they played online mini golf for about 5 or 10 minutes and then came back and we did the evaluation. So here we played the alarm, had them say what they thought it was, and then went on to the next part of the experiment. Now, participants completed what we call the memory assessment phase, either hearing entirely flat tones or entirely percussive tones. And at that point, they converged on our main task, which was the annoyance task. So here we played either both a flat and a percussive sequence and asked which one was more annoying. And then in half the trials, we also played 2 flat sequences or 2 percussive sequences, and here we used different pitch patterns. So our main point of interest here is how the difference pans out between these 2 different shapes of sounds. And so when we look at the data, when we crunch it all up, we can see a very clear pattern. So the key question here is that which of the sounds is more annoying? And what I've got on the y-axis here is the proportion of the ones they chose. So for the participants that heard the flat sounds when they were doing the memory assessment training, they still chose the flat sounds as more annoying over 60% of the time. For the ones who heard the percussive sounds, it was an even more striking difference. Now, I'll come back to why I think we might have a difference based on the training here, but the important thing is that on balance, about 80% of the time, people are agreeing that those flat tones are more annoying than these very easy to produce alternatives. Now, that first experiment used those pure tones. We did this again with more complex sounds, a little more musical sounds, and found essentially the same thing. And that's helpful to know from an engineering standpoint because we can use these sounds with more harmonics or more complexity without sacrificing the annoyance gains. So in terms of that difference between the 2 different kinds of training, we wanted to go back and look at that more because I think it has to do with the exposure, or something called a mere exposure effect. So we added a second annoyance task here, and we ran this annoyance assessment before anyone trained on either of the sets of sounds. So in the third experiment, we had this first annoyance, which we called the time 1 assessment, and we also had a time 2 assessment of annoyance, which was common across all 3 experiments. So now I've got the information here from the second experiment, and I can show you when we did the similar thing in the third experiment, now we had broad agreement, regardless of training, that the percussive tones are significantly less annoying. And because we had these 2 points of time to assess the memory, we can also look at what happened in terms of the difference between the first and second time. And so I'm going to add in some color coding to show you where participants differed between their first evaluation and their second evaluation. But the main thing is that although some moved from one group, an equal number sort of moved back. So essentially, when you're familiar with all these kinds of sounds, it's very, very clear that the percussive tones are far less annoying. And I think the implications of that are pretty significant. Because right now, all across the province and actually all across the world, hospitals are filled with sounds that are making these more annoying sounds. Now, a lot of improvements in medical care are challenging because they're costly or require retooling or introduce other unwanted confounds. But the thing with the alarms here is that fixing them is trivially simple from an acoustic standpoint and actually very straightforward because we can change the temporal structure of the sounds without changing their melodies. And because these devices are ubiquitous all over the world, even small improvements in their design mean we can leverage meaningful gains in public health at very little cost. So when I come back to the questions I posed before, I think the really pertinent one is why do we keep using such bad sounds? How did we end up in this really awful state? I think this really comes from a 2-part problem. So the first is just historical. In the early days of these machines, the bad beeps, the simple beeps were really all we had. That was what we were able to synthesize at the time. And we got used to machines sounding like that and just haven't really thought about how we could update them since. But the thing is, medical technology has advanced incredibly over the past several decades. I mean, it's not your grandfather's operating room that you step into these days. So why is it the sounds that seem to be stuck in the past? So here, I think we have to recognize a distinction between what's important in an auditory experiment and an auditory interface. And I know that might sound like a complicated mouthful, so let me unpack you through another study my team did to try and clarify. Because if you look at the kinds of sounds that scientists choose to use in auditory perception research, we see a very clear pattern of a bias towards those simple flat sounds. Now, I stumbled into this issue years ago when I found a musical illusion that broke with decades of research on sensory integration. Specifically, I found percussionists could use certain body movements to trick audiences into hearing things that were impossible to do acoustically, and all the scientific research up to that point said that particular pattern of integration was impossible. As I got more involved with research, I realized I think the problem is that a lot of research is based on these flat tones, and those aren't anything like the sounds that we hear in music or really everyday life. So to try and figure out the depth of the problem, one of the first studies I did when I got to McMaster was a survey of every experiment that had been published in music perception up to that point. Music perception is one of the top journals in the field of music perception, and so we went through 212 different experiments with the goal of looking at the balance of percussive and flat sounds. Along the way, we found a number of other interesting sounds that were being used from animals and other kinds of simplistic synthesized sounds, but we found something really curious, which is that we had to make a new category of sound that I never would have thought about when we started. And we ended up calling this undefined, because we found over and over researchers would give incredible detail about many things in the experiment and absolutely no information about the shape or the temporal structure, specifically the amplitude envelope of the sounds that they're using. And ultimately, undefined was our largest category, with a third of the experiments giving no information about the temporal structure of the sound they used. Now, I remarked about this to a scientific colleague once who sort of looked at me smugly and said, well, maybe that's because you only looked at a music journal. And if you looked at a rigorous journal, then you would find much better attention to detail. Well, I just rotated off as the secretary for the Society for Music Perception and Cognition. So to me, I thought those were fighting words. And we spent many years going through over 1,000 auditory experiments from 4 of the top journals publishing auditory research to see if that 33% of undefined sounds in music perception was a uniquely musical problem. And as it turns out, when you go to the broader scientific community, it's actually a bit worse. So here we found 38% that are undefined. Well, I found that to be a delicious moment of retribution, and I was happy to go back and talk to my scientific colleague. Really, I think ultimately the undefined sounds, while the most surprising outcome, are definitely not the most important. Because everyone I've spoken to when I've described, say if you read an article and it just talks about a pure tone, would generally just assume that would be a flat sound, which I think gets at the whole problem that we just assume those are the sounds that you have to use in research. So I think the meaningful thing from our discussion here about improving auditory interfaces is that over 3/4 of the sounds used to study the auditory system are these flat tones. And we went back later and recrunched the data and put it in another context that I think is helpful too. So if we look at the sounds that come from events in the world, things like musical instruments or the footsteps from walkers, that serves as only about 10% of what we use to study the auditory system. And moreover, that 10% of sounds are basically only used in contexts where the experiment couldn't be done any other way. So for example, in this experiment looking at whether we could determine the posture of walkers from their footsteps, you can't do that with tone beeps because you need that real-world connection. And the same with instruments, and that same thing is true of almost every sound that we found that wasn't one of these highly simplistic sounds. And so while those kinds of sounds might have some value in an auditory experiment where you need precise control over the stimulus, in other situations where annoyance matters, or if you're interested in the real-world implications, then I think we have a more significant problem. So it was this work that led me to be interested in the differences between simple sounds and complex sounds, and that's how I was speaking at the conference when I met that medical doctor, where we came up with the idea of applying some insights from musical sounds to try and improve the problems with these terrible, terrible sounds in medical devices. So what I want to do now is walk you through some of the things that we're going to be doing in the future, because I think we're only just starting to scratch the surface of the beauty of complex sounds. Now I'm showing you here the amplitude envelope of a single note from a cello, and you saw previously it's much more complex and changing than those simple flat tones. But even this view here is really just scratching the surface, because this image here is almost like a shadow. And the way that two people might have a similar shadow, even though there's many individual differences between them, this representation of the amplitude envelope gives us something about the sound. And it shows us how musical sound is more complex than other sounds, but it hides a whole world of fascinating complexity. Now, scientists will use microscopes to see the complexity that might be invisible from the surface. And so we're going to essentially take the equivalent of an acoustic microscope now and pick apart this sound. And so if we think about it in a 3-dimensional representation, we're now going to look not just at the amplitude on the y-axis or the time as we go into the page, but also the overtones or the harmonic structure of the sound. And so when we think about it this way, that amplitude envelope, that overall summary is really a shadow that doesn't give us the full story of all the complexity of how each individual harmonic is moving and doing its own thing. They're all sort of working together, but that amplitude envelope really just gives us the collapse of how all these come together. So when we look at sounds like this, you can see that each one is this amazing, beautiful sort of symphony of individual components. And I'm sorry, I warned you at the beginning that I'm an audio geek. I love looking at musical sounds like this, and I can tell you it's not just the cello that has this complexity. So all musical sounds are complex, although the different components and the way they move are different, and that's one reason why different instruments sound different. And this is one reason why musical instruments are so fascinating, and musicians spend their lives devoted to producing slightly better or slightly worse sounds, and instrument manufacturers spend huge amounts of time and money trying to figure out the slight tweaks they can make to produce better sound. So when you think about this world of musical sound complexity, it's interesting to contrast the richness of these musical sounds with the kinds of sounds that we're choosing to use in auditory research. One of my favorite figures that I've ever published is in this Oxford Handbook of Music and Neuroscience, where I paired these musical sounds with this kind of representation of the tone beep. And you can see from the representation here that it's missing a lot of what's really interesting and rich about musical sounds. Now, in the context of experiments, that may or may not be okay, but when you look at how sounds are defined in medical devices, they're taking their inspiration clearly from these kinds of flat tones. And now if we know these sounds are really annoying, and we know that musical sounds are really interesting, then I think we're at a very bizarre juncture because we've chosen to fill our hospitals with the kinds of sounds that we know are annoying. And remember, annoying isn't better in this context, because the goal of these alarms is not to alarm, but to communicate. So they're auditory interfaces, and that's something that we need to keep in mind when we're thinking about ways to design them in the future. So to circle back to our earlier question about how we ended up with this world of terrible sounds we're inflicting on patients and doctors, I think it started just with the history, where those were the only sounds we could produce. And now the steering committees who are deciding what kinds of sounds we use in these devices come from a world where those are the kinds of sounds that are used to explore the auditory system. Now, since my team aims to balance using sound to understand the mind while also trying to use the tools of science to understand sound, this kind of problem, I think, is a little bit easier to see. So my background was actually in music performance. I had 2 degrees in percussion before I got interested in psychology. And so I always find these tone beeps almost like a little artistically offensive. And the idea that we're studying the auditory system with them has never really sat right with me. So I've been delighted to find this useful practical application where now we can use all my obsession with auditory sounds to actually save lives. I mean, when I sent my mom the TED Talk and told her about this project, she responded that she was excited because now, after many years, she could finally say her son was the kind of doctor that helped people. So it's nice to take this foray into public health. But the way I see it, we're at this important critical juncture. And as we think about a better way to move forward with the sounds, to me it seems pretty clear. A good idea would be take some insight from all these rich musical sounds that musicians have spent generations refining. Alternatively, we could go on the same path where we're using sounds that appear to be inspired by Homer Simpson. And while that might seem almost laughable when we frame it that way, if you're in a hospital trying to recover after surgery, which would you rather be surrounded by? What if your parents are trying to recover from a difficult surgery, or a premature baby who's trying desperately to sleep? So we've gone over a lot of material here and covered a lot of different things. And so if you remember just one thing from this talk, I hope it's this. Bad sounds cost lives. Not only have we seen this in the ECRI warning about health technology hazards, we have the FDA survey showing 566 deaths traced back to problems with the sound design. And moreover, for every unnecessary death by beep, we have patients who are stuck in hospitals longer than they have to be. We have burned out medical staff, more exhausted than they need to be, and it's all because the sounds, for some reason, have been designed more annoying than they have to be. So I think my colleagues and I have a good idea of what we can do to produce better sounds that can lead to better outcomes in hospitals. But fixing this kind of problem requires much more than just a scientific solution. So recently, I've been doing a lot of outreach and talking with politicians, media, doing podcasts, because I think solving this requires more than just figuring out the better sounds. It requires changes in regulatory commissions, and it also requires just greater interest from the general public and awareness that sound design in hospitals doesn't have to be that bad. Now, in addition to this outreach work, we're continuing our academic work, publishing in medical journals, and also reaching out to colleagues in engineering. Because as I mentioned before, although we're focusing right now a lot on medical design in hospital, these auditory interfaces are not just confined to hospitals. So they're used in trains and planes and navigation of ships and nuclear power plants. And there's many different ways in which improvements to the basic sounds can have broad implications. Now, just in the context of the medical device industry alone, Industry Canada evaluates this at over $6 billion annually. And we have a way here not only to contribute to the Canadian economy, but to actually help save lives and improve the quality of life and quality of care in hospitals where these annoying sounds prevent patients from sleeping and actually extend recovery time, adding more burden to an already overtaxed medical system. So I think it's a very important public health issue, and I'm really pleased to have this opportunity here from Sparks to share what I think is a really urgent message with you. So thank you so much for organizing this series and setting up this talk. Just wanted to also acknowledge the funding agencies that helped to make all this work possible. And most importantly, the wonderful team of students that are back in the lab, who I can finally see in person again, at least sometimes, who are making even more contributions right now as we speak to try and improve the sounds that we're hearing in hospitals. If you're interested in more information about this work, I encourage you to check out our website at maplelab.net, where we have information about the people in the lab and the projects that we're working on, and everything else related to what we're doing. We're also on social media now, and I recently even started my own Twitter account, so if you want more information, feel free to follow us on Facebook or Twitter, and I'm happy to answer your questions now about the ways we can improve the soundscape in hospitals.
Thank you so much, Michael. Questions, comments?
Yeah. So hi, this is Amar. Am I audible?
Hello.
Yeah. Thank you very much for your wonderful insights about this all sounds. And I'm currently working as advertising manager, Sonic Identity strategist in advertising industry. But I'm from India, and considering from this marketing perspective, these devices are usually purchased by hospitals, one time, the single time. And as we see, the noise ratio in the surrounding versus the sounds which are using for alert systems, I think that environmental sound also matters, because I have seen recently I'm associated with the hospital account, and the population over there is huge, and everybody is wandering in the crowded space, the patients and everything. And that's why I think this alert sound system, these tones has evolved to the effect of the crowd and the silence. Because if you consider about the European hospitals or the US or Canadian or Australian hospitals, these are much more quiet place. But in case of marketing angle, there are some countries like in this Africa or some Asian countries where the population is more, and hospital environment is totally different than these cities. So I think from marketing perspective, they have to think about such sounds so they can be recognizable in the crowd. So what are your thoughts on that? Like how we can establish into this thing? Thank you for this.
Well, thank you for the comment. If I understood, I'm not sure I followed everything, but in many places, you're saying outside of North America, one of the challenges for the hospital landscape is that there's a lot of noise and cacophony, and it's important for these alerting systems to be able to cut through that. So that makes it sort of a different challenge than there might be in hospitals in North America. Is that what your point was?
Yes, totally. Yeah.
Okay.
So
And
they
that's
have to assign, the common tones from all the overall, considering the word aspect, because their product is shipping to different countries, and they have to customize the sounds for that.
Yeah, and so that internationalization element is huge. So the essential challenge here is we want to design sounds that are detectable and alerting and informative without being annoying. And I think one reason why they're built with these flat tones is that it seems like the best thing you can do is jam the most energy in there to make it the most detectable. Now, this introduces a whole host of other problems, and you've got to balance detection and annoyance. So one thing that we're doing right now is actually experiments that look at that explicitly. So the question that this boils down to is, are those flat sounds actually more detectable than sounds matched for energy that have percussive envelopes? And what we're finding is that actually with the percussive sounds, you can detect them better than these existing sounds and noise. And we're looking now at also detection of that concurrent with speech tasks, where we're finding they're not harming speech, even though they're far more detectable. So your point is an excellent one, that we have to balance all these different considerations. And it's a good thing to remember that the situations in different hospitals around the world are going to differ. But as far as I can tell right now, what we're finding is that these sounds are actually more detectable, particularly in noisy environments.
Yeah, thank you for that. And just one last this thing, like, what is your opinion about playing some music along with the sounds at very low level, like when we experience in the malls or the shops where they have set this very small frequency where you can't be directly heard, but indirectly they recognize the sound subconsciously. So such kind of experience, what you do you think if we done with these hospital sounds, like playing some symphonies at very low level, or some music which uplift them, or can change their environment, like from seriousness to at least happiness. So what are your thoughts on that?
So there's a lot of, I think, benefits to listening to music in background or hospitals. I'm a musician, so I encourage people to listen to music as much as they can. So in terms of the alarms, the essential issue always boils down to this detection, whether it's noise, whether it's speech, whether it's a music. Those are the things that we have to look at. So yeah, I think music can be a very valuable part of recovery, and I encourage people to listen to music as much as they can. Do we have any other questions?
I have one. Well, it's really just being struck, when we have people come and do these talks, I'm always fascinated by the topic, but I rarely know if it's going to have anything to do with my own work. And it struck me how many sort of deep parallels there are between what you're doing and then a lot of the work that I do on how to really incorporate data into evidence-based policy, and this massive move towards using data dashboards, alerts, all of these things to measure performance within organizations, and the noise of it and the problems of design and sort of over identification of issues and information that really causes this absence of being able to see the correct signals. And so the parallels were just kind of blowing my mind as you were talking, and realizing that in some ways for organizations, they're a lot, it's a lot newer than hospitals in their relation to sound, and that there is more sort of early intervention possible to do the kinds of things that I'm teaching in my classes, and I'm really pushing for in terms of being able to incorporate what we know about psychology and artistry and all of that into the design, so that you're not basically creating the visual equivalent of these terrible flat tones, which is most of what performance measurement visualization is.
Yeah, that's an interesting point, and that reminds me. In the early days of these alarms, they contracted some sounds from someone named Roy Patterson, who is sort of an alarm design genius based in the UK, and he came up with a great set of sounds that were distinguishable and ticked all these boxes in terms of the perceptual qualities that we should have. And the fundamental problem that he ran into is that people just didn't like the way they sounded. And so because of that, they ignored those alarms, designed the ones that I showed for you now, and in that peer-reviewed apology, after acknowledging this was a terrible idea, they say we should have gone with the Patterson sounds because they were much better from a perceptual perspective. And I think it's an interesting cautionary tale, because the aesthetics often get seen as, a side note. In the context of an experiment, I can definitely see how that's the case, but when the focus is on information, like, it's not art, so the aesthetics don't seem that important. So here's a good example of where ignoring those aesthetics has actually led to some significant problems. And I guess that's another nice parallel to what you're talking about in vision, and I'm interested to learn more about that later on.
I know we're at time. If anyone else has a quick question, and Michael has another minute or two, we could probably take it. Otherwise, Thank you all for coming, and thank you so much, Michael. This has been fascinating.
Well, thank you. Thanks for setting this up, and thanks for logging in. Feel free to send me an email if anyone has further questions.
All right, take care, everyone. Have a great rest of your Friday.